This week, we're going to be reviewing our discussion of discrete log from last week and diving into probability theory and digital signatures. So we're going to specifically be talking about sort of an overview of probability theory, since probability theory is sort of the basis of how we derive the security of many cryptographic schemes. The emphasis this week is sort of on the techniques that we use to say whether a scheme is secure with some probability or is not secure. And to anyone who's familiar with a bit of probabilistic reasoning, this should be something of an overview and review of things that you might have learned in a previous course or previous job. But all of these sorts of techniques are sort of things to be firsthand familiar with when especially reading new cryptographic primitives or papers, as you will. So we're going to start off with a review of the solutions from last week. The solution or the exercises from last week were basically just getting practice computing on pen and paper the Elgamal algorithm and Shank's algorithm, which we covered in last week's session. So the solutions are up and they're pretty straightforward. So I'm going to leave them on the site for you to review in your own time. But I want to emphasize the sort of importance of getting your hands dirty with solutions. It's a lot easier to say that you understand something and not try the algorithm with fake made-up numbers. But when you sort of do the algorithm one time, it helps the staying power of the question much more. So on that note, if there were any questions about last week, now would be a good time to ask them. Otherwise, we're going to move on. Okay, so let's carry on here. So this week we're going to be talking a bit about probability theory. And I want to draw attention to a slight change in schedule for next week. I'm going to be getting on a plane in the middle of the day next week on Friday, so we're going to start 75 minutes early, so I have plenty of time to make that plane. Moving on here. This week we're going to be talking about probability theory and digital signatures, as we mentioned. The main things to highlight excuse me. The main things to highlight, I think, that the book doesn't necessarily highlight, are that when we think about cryptographic security, three generic classes of security that we sort of consider are whether something is perfectly secure, statistically secure, or computationally secure. So the sort of emphasis here is that very rarely is the perfectly secure, that is, an adversary gains 0 bits of information by looking at the ciphertext. Perfectly secure schemes that are also efficient are quite rare. And an exception to that rule is Shamir's secret sharing scheme, which is both efficient and perfectly secure. And in a Shamir secret sharing, if you were to say split a private key into n different shares of the private key, where you need at least some fraction of those shares, some threshold t out of n of those shares to reconstruct the secret. You can do that with a technique called Shamir's secret sharing, which under the hood, Shamir's secret sharing is really just Lagrange interpolation. But the point here is that very rarely in cryptography do we get a scheme that has both perfect security and is quite efficient. A sort of good example of the perfect security is not efficient is the one-time pad, where often we want to use a key for, say, a key of 1024 bits for, say, up to 2 to the 32 bits of message encryption. So the ratio there on key expansion is pretty good for the sort of asymmetric encryption algorithms and symmetric encryption algorithms, whereas one-time pads, you need to have a 1-to-1 ratio between your key and your message length, which is quite inefficient. Another example of where this sort of question of computational versus statistical binding comes in, or computational versus statistical security comes in, is the premise of Pedersen vector commitments. And I could have also just talked about Pedersen commitments, but we generally think about Pedersen commitments as a way for someone who wants to prove that they have access to some secret information, say a secret key X, or the coefficients of a polynomial. A Pedersen commitment allows that party to say, I'm going to bind myself to this value, this secret key, or this vector. Excuse me. I'm going to bind myself to this value, or this secret key, or this vector. And everyone else that is watching knows that the party who has committed can't change their value underneath the commitment. So that's what binding is. But it's worth asking, what kind of security does binding obtain? So we need to think about two things. We need to think about, well, first, the party that committed, they should not be able to change their value underneath the binding. And second, every other party should not be able to see the value that the party committed to. If the value is in a commitment scheme, we think of the commitment as still being private. So this has a lot of similarity to sort of hash, in that the first step of the commitment, the commitment itself, that binds the party to some pre-value. If we think of a hash function just takes some pre-image, say mapping X to some output of the hash function. It would be difficult, it would be violating collision resistance of the hash function if the committer was able to find some X prime that changed their commitment to some other value underneath the commitment. So that is sort of pre-image, or sorry, collision resistance. Now, what kind of security would that have? So what would it look like for it to have statistical security that the committer could not change their value? And after thinking about it a little while, you should maybe arrive at a type error. Because when I say type error, I mean this is sort of applying the wrong model to the binding, because the adversary cannot distinguish between statistical security is the sort of statement that the adversary cannot properly distinguish between one probability distribution that is the ideal probability distribution and the other, which is the actuality of whatever the party protocol participant is doing. So the adversary in this case is the committer themselves. So the committer themselves could not necessarily distinguish between their own commitment and an alternative pre-image. These things just sort of don't make sense. So the sort of type of security that we would be pursuing in this case is we're looking for some argument that the committer would need to search through at least so many values and could only find a value that violated the collision resistance of this scheme. We want to put a probabilistic bound on that. And of course, the brute force method, if we would expect a collision in 1 out of every n values, then we would estimate the security to be roughly on the order of n. And so now we're talking about security parameters. So I hope that made sense. And the second type of security that commitment schemes sort of have to analyze is the hiding property. And this is that to every party that isn't the committer, if they see the commitment, they shouldn't be able to get from the commitment back to the pre-image of that commitment. And so this is just pre-image resistance. So if we return to our hash function analogy, if the adversary can distinguish the output of the hash function from randomness, then they have information about the plaintext or the pre-image. So in this context, statistical security does make sense. In that, excuse me, in that the adversary is interested in finding any degree of difference from a random distribution. If the hash function reveals information about the preimage based on some statistical bias in how the hash function produces results, then the adversary can distinguish the output of the hash function from randomness and get clues as to the preimage of the value. So a secure commitment scheme, and equivalently a secure hash function, would be statistically sound or statistically secure, in that an adversary would not be able to distinguish the output of the hash function from pure randomness. But even if the adversary could distinguish the output from randomness, but still could not obtain the actual preimage, we could say that the hash function in question was computationally computationally sound or computationally secure. But in this particular case, it would be a sort of weak claim, or a much weaker claim, to say that it was computationally secure than to say it was statistically secure. So we might expect our hash function to be statistically secure. And if, what do we got else? Finally, okay, yeah. The last thing about Pedersen commitments that's quite significant is that, well, obviously, if the committer revealed X, the preimage to the commitment scheme, every other party would believe that X was the value committed to, because they could check for themselves and compute the hash function on X for themselves. Pedersen commitment's sort of special feature is that we can use them to generate a proof of knowledge of the value of X without actually revealing X. So this is a type of zero knowledge proof. So the counterparty, the verifier of this proof, needs to sort of have, similar to the first scheme, if the verifier can extract information about X from the proof, then the proof is not statistically secure in the secrecy of X. But if the prover can lie about the value of X, that is, they can generate a false proof, then that would be not computationally secure. And usually statistical security, when it is something that applies to the given model, is traditionally stronger than computational security. Hopefully some of that made sense. We're emphasizing this on the basis that I think the sort of introduction to probability theory in the textbook gives a lot of context for probability theory, but maybe less context for cryptography in that sense. So let's go grab the book here. So the basic concepts of probability theory are sort of all covered in this section. And the section is kind of meandering. All of the parts in this section should be reasonably familiar to you if you're sort of looking at trying to understand the security of a cryptographic scheme yourself. I think it covers sort of all of the topics from, or several topics that are sort of like basic definitions, sample spaces, and conditional probability and events. And I think there are several fairly high quality introductions to probability theory on the internet. So if you find that this writing doesn't suit your tastes, probability theory has been discussed to death, especially with the rise of machine learning stuff of late. Everyone is a statistician now, it seems. So I think I wanted to present one example to give several flavors of techniques that we sort of might use when solving a probability question. I know this is probability theory in a nutshell. It's really just one example. So somewhat misleading to know. I'm going to check. All right, so this should be sufficiently large. So we're going to revisit a sort of classic question. So The question is, if we have a bunch of people that deposit hats at a party into a hat closet, and they get their hats back at random, what is the probability that at least one of these people get their hat back? So at start, like we might think, well, what's the probability that I get my hat back? Well, if there's n people who went to the party and everyone gets their hat back with a random probability or with random chance, I know that I'm going to get my hat back with 1 out of n chance. So the probability that at least one person gets their hat back is obviously going to be at least 1 out of n. Now, what's the probability that everyone gets their hat back? Well, that seems like it might be a much lower probability. But we're going to try to answer the question, what happens, or what's the probability that at least one person gets their hat back? So we need to start by defining things that happen in our sample space, things that are interesting. So we take our universe, omega, and we define some events. And the events that we're specifically interested in are, well, did at least one person get their hat back? So we can sort of index our events 1 through n. So if person 1 gets their hat back, then event 1 happened. And our events are not mutually exclusive, and they're also not independent. Because if person 1 gets their hat back, then person 2 will get their hat back with 1 over n minus 1 probability, as opposed to 1 over n probability. I'll pause for a second to make sure that that sinks in, that these events are not independent. They're correlated in some sense. So we can't do an extremely convenient thing. If they were all independent, we can just say, well, add the probability that each of these events happens, and then we've solved the problem. But since they are correlated, we have to do something slightly more sophisticated. So we then can say, well, if the events that we have described, E1 through En, are all of the events that we are interested in, we want the union of all of these events. So let our sort of point of interest, our event of interest, be A. That's the sort of thing that we're curious in calculating the probability of. In fact, we're interested in calculating the probability of 1 minus A, because we want the probability that no one gets their hat back. Where PA is the probability that at least one person gets their hat back. So we can express PA. And this is a fairly common trick from combinatorics. Once we've defined our sample space, the events that we care about, and we have our defined sort of point of interest, we want to find some way to express what is the proportion of events that fall into A, and what proportion does not fall into A. And an easy way to do that in a sort of combinatorial setting is that we just say, well, if all of the outcomes happen with equal probability, and some of the outcomes, we can list out some of the outcomes, so the number of ways that at least one gets their hat back over the total number of ways that this could all pan out. If we wanted to tackle the second one, the total probabilities first, and you have people where we have some dots here. Obviously, if these hats are going to get randomly reassigned, and these are going to be hats here, this is just a question of permuting the dots. And so if you had 4 dots, then you have 4 factorial ways to permute the dots. So in total, the number of ways to permute the hats, to reassign hats to the people who leave, is just n factorial. So if we're interested in answering the question, so how many total possibilities could happen? well, we have the simple argument that we just need to permute all of the elements. So out of all of the things that could happen, and there are n factorial ways. And so second, we try to answer the slightly harder question, like how many events are inside of our inside of A, how many events satisfy our sort of interest criterion. And we can sort of start thinking about this in cases. So what happens when exactly one person gets their hat back? Well, let's say pick person at index 1 or index 0 and assign them their hat back and permute the remaining n minus 1 hats however we want. Well, then we can say fairly easily it's just going to be fixing the hat at index 0 and any permutation on indices 1 through n minus 1, then that's n minus 1 factorial ways. And since we could have picked any one person, we could have picked and choose one values, then the total value for exactly one person gets their hat back might seem to be n factorial. But that should be suspicious to some of you. And it turns out that we've double counted a bit. Now, if we take the preceding argument and say, well, person at index 0 gets their hat back, and we're going to do some arbitrary permutation on everyone else getting their hat, well, then that arbitrary permutation at least included the possibility that everyone else got their hat back, no one else got their hat back, one other person got their hat back, and everything in between. So when we go on to index 1 and we fix index 1, person 0 is going to get their hat back again in some of the new experimental results. So we've double counted at least all of the ways that two people get their hat back. So we need to subtract out the ways that two people get their hat back. But then after doing that subtraction, we sort of run into this recursive issue. We then need to add back the number of ways that 3 people got their hat back, because it turns out we've overcounted again in the wrong direction, and we sort of get this sort of what is referred to as the principle of inclusion-exclusion thing going on. Let's see if I can slide over here. So the principle of inclusion-exclusion is that oftentimes we'll have a situation where if we want to count the union of events, oftentimes we get well, here's the sort of relationship that we end up with going with anyway. Is that we're going to sort of start with n factorial events, then we're going to lose all of the ways that we overcounted the number of 2s, and then we're going to regain all of the ways that we just undercounted the number of 3s and so on, up to the point where we need to remove all of our values of n. So this is a fairly neat trick when we think in probability theory terms. It's that we sort of can express all of these sort of countings through this principle of inclusion-exclusion. And once we have a sort of closed formula, there's usually some convenient operations that we can do to reduce the situation. So in this particular situation, the convenience is that we can cancel n minus 2, n minus 2, n minus 3, n minus 3, and so on, and come out with just this formula. And this formula is actually not maybe the simplest to look at, but if we notice that we're now going to run back into our original question of how many number of ways satisfy our criterion over the total number of possibilities, we're going to take this all over n factorial, and all of the n factorials in the numerator disappear. And then to compute the final probability, we can just take an estimate and say, take the first 3 terms here, and say that 1 over 2 plus 1 over 6 minus 1 over 24 is about, is 0.375. So we can take a sort of approximation when solving probability theory situations. But the problem goes on. And before we go on, I want to ask and stop for questions. So if there are any questions about the last 10 minutes, uh, speak up. All right. Cool, cool. And I wanted to highlight before we move on from this problem. There is a little bit of cool math here that I couldn't resist showing off. So at the end we took this approximation scheme. We can obtain a much more interesting result from a mathematical perspective by remembering some calculus. And you might remember the Taylor series or the Taylor polynomial from your sort of calculus, high school or college calculus class, that we can compute e to the negative x is the evaluation of f of x evaluated at some point, plus the evaluation of f's first derivative evaluated at some point over over 1 factorial or 2 factorial, and we can kind of continue that, which is the Taylor series. And the Taylor series for e of x is particularly striking. It's if we evaluate the Taylor series polynomial here, we get x x minus x over 1 or x over, we get this sequence here basically. The Taylor polynomial for e to the negative x. And this should look familiar. This looks quite similar to what's going on over there. If we plug in 1 for x, then we actually have almost precisely the same expression. The difference being that our sequence doesn't end at n here. This goes on infinitely. So as n gets larger, the solution for this problem will approach simply the value of e to the negative 1. And as we see, like 3.68 is pretty close to 3.75. So as n increases, the value or the probability that you get your hat back will converge to e to the negative 1, which is a sort of neat mathematical trick. So hopefully that was an interesting tangent. There was one thing to take out of that. We're often looking for interesting sort of applications of cross-domain sort of mathematical tricks when solving mathematical problems. And they might not be particularly obvious, but once you sort of develop an intuition for looking at sort of mathematical writing, you tend to develop a sort of intuition for where a sort of sequence or trick from another domain might be useful. All right, let's grab the book. Now, we're going to mostly skip over section 4.3 in the lecture and leave it as an exercise for the reader. But it's a well-recommended exercise because it will give more familiarity with the content that was discussed in that example. So let's continue on to signatures. So if we wanted to talk about signatures, signatures are often presented as sort of the inverse of encryption, in the sense that encryption you encrypt with someone's public key and they can decrypt with their private key. Signatures is a one to many, and encryption is a many to one. So they're sort of like natural inverses of one another or converses of one another. In the case of RSA signing, it's almost exactly just the same operation. You just, instead of exponentiating by the private key, you exponentiate by, or instead of exponentiating by the public key to encrypt, you exponentiate by the private key to sign.
but RSA signatures and RSA in general are sort of slowly being moved away from by the industry. RSA is sort of well known to be um, or well known to be unlikely to be correctly implemented. There are lots of holes in it that can leave many implementations sort of insecure, even for fairly production services. So RSA is not heavily relied upon, especially for recent years. In the blockchain context, in particular, I don't think RSA signatures are used on any chain. They're all using ECDSA or EDDSA or BLS signatures. And we'll be going into sort of how those differ right now. So the book does not cover, if I remember correctly, the book does not cover EDDSA, or EDDSA is the same thing as Schnorr signatures. So the book does not cover EDDSA signatures, maybe because they probably wouldn't have actually been that popular in 2008 when the book was published. But since the book was published, the patent on Schnorr signatures expired in 2008. So in the meanwhile, the Schnorr signature scheme is both simpler and more efficient than ECDSA signatures, and it's grown in popularity. I think the recent Bitcoin Taproot network upgrade was specifically to add support for Schnorr signatures so that they could use some interesting adjustments to the Schnorr signature scheme to implement adapter signatures. Schnorr signatures also lend themselves to easier threshold signature schemes, which we'll talk about a little bit in week 14 or 15. So just in a nutshell, to get a sort of raw sense of things here, in the Schnorr signature scheme, in both schemes, the signer computes some ephemeral nonce and computes some value. But in the ECDSA process, the value includes this term of k to the negative 1. Whereas in the Schnorr setting, there is no value of k to the negative 1, which makes this a simpler process for computing signatures, simpler and more efficient. So in practice, Schnorr signatures tend to be both easier to sort of incorporate interesting cryptography primitives into, but also more efficient to compute because of that. The verification step is also simpler. So the sort of side-by-side comparison is laid out here for you if you'd like to peruse that at your own rate. But the main things to take out of this is that these are basically the two most common signature schemes. And the main sort of incentive to move away from ECDSA is not really that it's insecure so much as the presence of this k to the negative 1 component makes it quite difficult to manipulate into other sort of signature adjacent primitives. So to answer a question from the chat, aren't implementation issues a problem for all signature schemes? Yes, implementation issues are a problem for not just signature schemes, but all of cryptography and most algorithms in general. But RSA has plenty of sort of bad values. There is a plethora of ways that a value can be sneakily bad in RSA. The premise for RSA being insecure or difficult to implement more correctly, is that it's been shown repeatedly that implementations of RSA have left sort of subtle vulnerabilities. So the entire industry has gradually moved away from RSA over time. Let's continue.
And I have just two confirmations here.
Yeah.
the difference between, or why we can't have like Schnorr signing on, let's say, Ethereum's curve is specifically because of the elliptical curve we chose, right?
Yes, that's my
Okay.
understanding. Um,
And then,
or
oh no, sorry, if you're going to finish that thought.
it would make the curve more efficient if you could still use a Schnorr signature scheme, but you will notice that or actually, I'm not sure exactly what makes the Schnorr signature scheme less efficient on, what is Ethereum on?
SEC,
BN or
SEC,
yeah,
yeah, SEC.
SECK 256.
Yeah.
Yeah. Uh,
Okay.
yeah, I'm not actually sure what makes it inefficient on the curve, so you might want to take my yes with a grain of salt. Um,
Awesome.
yeah,
The second thing I had was around that K value, and you mentioned like that's something where it's a bit
yeah,
harder,
yeah,
or it's like computationally more expensive. There's this thing around like deterministic signatures. Is that also what makes this like in? I've heard the like non-deterministic signature for ECDSA. Is it that K value that makes it like non-deterministic?
yeah. Because K is the blinding factor, and it's effectively an ephemeral
Okay.
key. So I'm not entirely sure. I'm not super familiar with deterministic signature schemes or what they're used for. But yeah,
Okay. Awesome.
the value of K is probably the main contributor to it. Um, Hopefully that was helpful. Before we
Very
sort of
helpful.
move on, are there any other questions about signature schemes that I might be able to answer? Okay, cool. The I think, mm, yeah, I think the main piece to take out of in this section is going to be um, get some practice implementing or doing by hand a signature scheme, and you'll sort of see how these pieces move together. A lot of the time, something makes more sense if you can derive it for yourself on paper or on a whiteboard, especially if there are several moving parts. Um, and I think that's going to be nearly it for this session. It's a bit of a shorter session. I could cover some of this section in the book, but I do feel that the reading for this week would probably do as well of a job of me reading the textbook back to you. I think the one main thing to take out here is the signature schemes can be sort of good tests of your ability to understand whether or not you understood probabilistic security. If you start thinking about what's the probability that an adversary could recover any information about the input to the signature scheme or the message. Since the message is public, you can sort of use signature schemes or encryption schemes as sort of like your toy example when you're thinking about probability theory. Um, and maybe a preview to next week. Next week we'll be talking about um, yeah, next week we'll be talking about the chapter 5 on elliptic curves. And I think we will be, or as I mentioned, we'll be starting 75 minutes early next week so that I can make my plane. And there are, in addition to chapter 5 in the book, there are some resources that are recommended in next week's course notes if you wanted to take a sneak preview. Yeah, let's see. Anything else? There are 3 exercises assigned for this week. The I think most interesting sort of exercise is going to be playing the Kelly criterion game and rederiving this sort of theorem for yourself. The Kelly criterion game is a sort of betting game and is another good example of sort of an interesting problem in probability theory that's sort of illuminating to solve and gives some good practice in solving this sort of problem. Um, Finally, there is a bit of homework in reading over the Rust crypto standard K256 implementation. And this is sort of meant as a primer for getting ready for next week when we start talking about elliptic curves more. So, yeah. Maybe one more stop for any last questions before we close out. All right. Thanks everyone for coming. And I hope you have a great weekend.
Thank you. Thank you.
Thanks so much for the lecture. Have a great weekend, everyone.
Thank you.